Hello everyone and welcome back to Thermo Shorts, where we're trying to distill the main ideas from the big lectures that we're giving in class and are posted on YouTube. So lecture 4 was about work and power. So we've sort of introduced this idea that the first law can help us understand the universe. So we take the universe, right, which is this big blue blob in my schematic here, and we separate it into two parts. The system, which is the part of the universe that we're most worried about, and the surrounding. So in order to solve the first law, there's a couple questions I want to ask myself. What's in my system? Is it air, or is it water, or is it something else? Is the system open or closed? Can mass move in or out of it? In the first third of the class, the system will always be closed. How much energy does it have at some initial time, if we're talking about a closed system process that's moving through time? How much energy does it have at the end of that process? And how did that energy change happen? What process happened to my system? How much of that energy change is due to heat transfer, and how much of it is due to work? Now, as you may have guessed from the title of this lecture, what we're interested in here is how do we calculate work, particularly in closed systems. So you may remember from maybe an undergraduate physics class or from engineering mechanics that work is force times distance. But if you had a pressurized fluid that was pushing on a piston, like we're showing in this picture here, what happens is as that gas expands and pushes the piston, the pressure drops, which means the force is a function of the distance that the piston has traveled. So here, we could take the work and integrate from the piston's initial position to its final position over sort of the sum of these infinitesimal small distances dx. And if we did that, we could find the work. But we also know that the force that pressurized gas was applying on that piston is equal to the pressure times the area. So I can substitute this force with pressure times area. Now, both pressure and area could be functions of x, right? So I put this substitution into my equation, and I get this equation here that work is equal to the integral of the pressure times the area times this length dx. So what can I do here? I can notice that this area times dx, so that's the cross-sectional area shown in blue here, A, multiplied by this infinitesimally small distance dx. Now what do you get when you take an area times a very small distance? You get this infinitesimally small volume. So if we make the substitution that A dx is equal to dV, this differential volume, then our relationship for work is the integral from the initial volume to the final volume of pressure times dV. And if I could integrate from my initial volume to my final volume, then I would get the work that the system is doing on the surroundings. Turns out this is a very important relationship, particularly when we're dealing with closed systems and we want to find the work that the system does on the surroundings. But in order to use this equation, we need to know how P is a function of V. We can analyze this problem for the constant cross-sectional area, but also for an arbitrary cross-sectional area whose area is changing as x changes, because we're now just talking about this dV term. But in order to use this equation, we need to know pressure as a function of volume. Now in thermo, we'll often model processes as being polytropic. So that means that pressure times volume to some exponent, which will be specified for a problem, and we'll talk about physical meanings of different exponents here, is equal to some constant. So if I know that, then I know that pressure is equal to that same constant divided by V to the power of n. That's an equation that I could plug into my expression for work do a little bit of calculus, and find the work that the system does on the surroundings. And that's exactly what we'll be doing as we move forward in the next couple of lectures. So, to conclude this lecture, we did this problem. Now, this problem, the calculus here is not exceptionally difficult because the pressure is constant, which means we can take it out of the integral. I won't work through the example here. You can go back to the full lecture, or you can just try to do this problem by itself. Thanks for joining me on Thermodynamics Shorts. I'll see you next time.